Okay, so thanks everyone for having me here in this meeting, and thanks to the organizers for allowing me to give a talk in this conference, and hopefully in the future, near future, it will be in person. So today I want to tell you about work I've done with Michael Pretko on Fracton-like quasiparticles in hole-doped antiferromagnets. For the most part, this work has been done at Columbia University, and it appeared in NPJ Quantum Matter and PRB in 2020. So I want to start by the take-home message. This is what I would like for you to get out of this talk, even if you miss some of the details. The goal of this work is to find implementation of fracton conservation laws in hole-doped antiferromagnets. So what we will find is that in certain systems, in certain antiferromagnets, we'll have quasiparticles that are very reminiscent of fractons and dipoles. The fracton would be a one hole coupled to the magnetic background. The dipole will be two holes coupled to the magnetic background. And this will give us robust fracton-like behavior. It will be exact in what I call the mixed dimensional 1D limit. It will be approximate in 2D and 3D, and it will be relatively stable to certain small perturbations. I'll define what I mean by that. And for the purpose of this talk, what I call fractons and dipoles are quasi-particles that have or obey the symmetry, the constraints, the mobility constraints from the global symmetries of fractons. So this is very different from the gauged models that you get in 3D or from House code, for example. Okay, so let me start by the objective. The objective is to get fractal realizations in realistic systems. And so just a reminder, probably everyone here knows that. What's the physics of fractons? I'm basing this on Pretko's PRB in 2017, where if you consider rank 2 symmetric tensor gauge theories, where the density has two derivatives of the electric field, you will find that besides charge conservation, you will also get conservation of dipole moment. And what that implies, as discussed by Pretko, is that there will be severe restrictions on the charge dynamics. Not only you will need to conserve charge in the system, but the movement of charge is constrained. For example, the fracton, which would be a single charge in this picture, cannot move, because if it moves, it will violate dipole conservation. However, a dipole, which is defined as a bound state of two oppositely charged fractons, can move together. This will still conserve dipole. And so how do we get this in realistic systems? This is interesting to have, just to look at properties of these systems. There are proposals using large external electric fields by Kamani et al. And Guardado Sanchez et al. I am more interested in intrinsic mechanisms. By that I mean, can we take a system where it's not obvious that these conservation laws would be present, and then look at their interactions, and then somehow they give rise to these conservation laws. So there is one example that's been discussed before in the literature and been brought up again in the context of fractons by Mudgalaya et al. In a 2019 paper, where they discussed the thin torus limit of the quantum Hall effect. But in this talk, I want to focus on a different system. Here I'll focus on holes doped into antiferromagnets, and the final result will be that the single hole will have properties very similar to the fracton, and two holes will have properties very similar to the dipole. So the physical setup, as I said before, hole-doped antiferromagnets. I'll discuss 1D and 2D models. Classical antiferromagnets, so the magnetic coupling is Ising. And I will look at single hole and interactions between holes in this context. So let's look at the single hole. We can just take the 1D problem first. There aren't really true antiferromagnets in 1D, but we just can, as a setup, we can try. And if you took a hole and you dope it into antiferromagnet and you just allow the hole to move, the spin will move here. So you'll get a frustrated bond because this spin is obviously not happy if it wants to be antiferromagnetically coupled. But then after this, if you try again, you will find that essentially all subsequent hops will allow the hole to move freely, And so you can't really say that this is a fractal-like behavior. There's just an energy cost, but then after this, you're fine. So we need to work harder. We can go look in 2D. where you can have real antiferromagnets, and you can look at the squared lattice, for example. And then here I'm showing you one process where I can move the hole over and over in the background. So the first time I moved, the spin came here. I actually frustrated 3 bonds. The spin is unhappy. I can do another hop, let's say in this direction. This spin comes here. Now there are 2 frustrated blue bonds. I can do this again. I bring it here. Now there are another 2 frustrated bonds in red, one you see and one you don't see. It's out of scope. And then you do this again, and the hole comes here. And then this one now is also unhappy with this one and another one you don't see. And now the hole can move again and start healing the background. So when the hole is moving here, it brings this here. There are 3 bonds now relieved. And then I come back here and all the bonds are happy. So that just means that there is a very large energy cost that appears at 6th-order perturbation theory, where the hole can finally find a way to move away from its original site. This has been discussed before by Trugman in the context of high TC superconductivity, but for the purpose of this, it just shows us that there's a parametric range or a parametric regime where the hole is essentially localized, but eventually the hole will move. So this gives some hope that there will be Fracton-like constraints. But we can do better. So we consider the mixed dimensional limit. I forgot to cite the paper that introduced the terminology of mixed dimensional. Mixed dimensional essentially means let's take a 1D model, but in a 2D background. The purpose of this is that now, if I allow the hole only to move along a line, I will find that every time the hole moves, the background is getting frustrated. The first time was obvious from before, but now as I bring this here, because there's this spin up here and spin here too, in these 2 directions, in this direction to the right and to the left, uh, the spin is getting frustrated. So essentially moving the hole to infinite orders will require very high energy cost. So the hole becomes perfectly localized. Uh, and so that is an exact realization of fractal behavior. How do we do this? We can apply a gentle field that essentially constrains or forbids energetically the motion along this direction. And then you can essentially realize this in systems. And I believe this has been done to some extent in cold atoms. So the summary of the single hole physics is that essentially you can get exact fractal-like behavior in mixed dimensional 1D limit, approximate in 2D and 3D, and existent in strictly 1D. However, this is not sufficient. We need to look at 2-hole physics to see if the interactions allow dipole motion. So in a sense, the result of the hole is surprising because the original model allowed the hopping of the hole. But somehow, because of the coupling to the background, the hole does not want to move if we consider the appropriate limit. If we look at 2 holes, it's obvious that the 2 holes will form a bound state if they're on different sublattices and neighboring, and that bound state will have dipole-like character. For example, if you look at this configuration, you can move the hole here, you bring that spin here, it's unhappy because there are 2 bonds that are frustrated, but then this hole can hop there, and now the 2 holes are together, the background is happy, and I have a bound state, and you can compute its energy and show that it's actually lower than the 2-hole state, the free 2-hole state. And if you'll see that in this subspace where you have no frustration of the background, this effective subspace, essentially the 2 holes conserve the relative distance. So that is a perfect analogy with a dipole. The 2 holes have different spins. We can, pretend that the spin is our effective charge. And in this fashion, we can say we have fractons, which are single holes, and dipoles, which are bound 2 holes. And this physics happens in the mixed 1D and in the 2D limit. So just to give you a fast review, I told you that in the mixed dimensional antiferromagnet, I have a fracton, which is a single hole coupled to the background, a dipole, which are 2 holes. And then in the general 2D limit, this behavior is the same, except that for fractons, it's approximate. There are violations of 6th-order in perturbation theory. And so why is that interesting? It's not obvious that you could have got that in antiferromagnets. Also, this behavior is stable to drip perp. So if you want to have a more realistic model where you have spin exchange, it will be stable to leading order in T over JZ. JZ is the Ising coupling. So, there's some hope that this parametrically could happen in materials. There are also materials that are in the Ising limit. We discussed this in the papers. And this setup allows us to look at some finite density physics of fractons that has been discussed, for example, by Prem et al. In a PRB in 2018, where you can have emulsion physics in this language that will be just phase separation and similar kind of questions. So I hope that I am finishing early, but I guess that may be good for questions. So to summarize, I told you that there are quasiparticles reminiscent of fractons and dipoles. A fracton in this context is one hole coupled to the magnetic background. A dipole is a two-hole state on neighboring sites coupled to the magnetic background that gives us robust fracton-like behavior. So by that I mean, we showed that we can do this in an exact fashion in the mixed dimensional 1D limit, but it will be approximate in 2D and 3D. It's relatively stable to small J perg. And in fact, which I have not discussed here at all, there's a family of coupled fermion boson models where this behavior exists. And we discussed this in detail in the PRB paper. There are a variety of models where you can do this. And there are even models that are not discussed in this paper, but it's clear that this behavior will exist where the single particle does not want to move, the pairs want to move and conserve the relative distance. And one interesting future direction perhaps is to find if by playing with the couplings and looking at complex lattice geometries, one can get Lennon-like quasiparticles, a quasiparticle that the dipole will move, the fracton only moves along the line, for example, or what would be reminiscent of a fracton moves along the line. And thank you for your time.
Great. So thanks for finishing early. We'll take a short break and then